Chapter 13 Wildfires. Here is a natural hazard close to home. This picture is of the Trinity Ridge Fire, August 24th, 2012. The late summer of 2012 was a smoky one. It was hard to see downtown Boise from the freeway. I know, my eyes and lungs were not the only ones irritated for about a month due to super bad air quality. On August 14th, the Moderate Resolution Imaging Spectroradiometer, MODIS, on NASA's Aqua satellite captured this image of the Idaho fires. Red outlines indicate hot spots where MODIS detected unusually hot surface temperatures associated with fires. The three red spots from top to bottom are called the Mustang Fire, the Halstead Fire, and the Trinity Ridge Fire. Causes of the Mustang Complex and the Halstead Fire was lightning. The Trinity Ridge Fire was started by humans. According to statistics maintained by the National Interagency Fire Center, a total of 548 wildfires had burned 790 square miles of land in Idaho that year through July 29, 2012. The Mustang Complex fire had burned 149,828 acres of rugged terrain near Salmon, Idaho by August 29, 2012. The fire burned in steep, inaccessible terrain, making it particularly hard to fight. The image shows the hot spots of the Mustang Complex outlined in red and the smoke plumes as of August 28, 2012. By August 29th, more than 8,392,209 acres had burned throughout the United States in what was proven to be one of the most severe wildfire seasons in the last decade. By September 11th, more than 1,529,715 acres had burned in Idaho, more than any other state in the nation. The image shows hot spots in red and smoke, especially smoke in valleys, along the Idaho-Montana border on September 13th, 2012. Obviously, not all years are quite as bad in terms of the wildfire hazard, but every fire season has the potential to influence my recreation and my health, and yours too. 13.1 Introduction to Wildfires. The wildfire hazard hasn't always been a natural hazard on the earth. We first had to get enough plant material to burn. About 350 million years ago, trees spread across land and wildfires began to occur. About 20 million years ago, grasses spread across land, making wildfires more frequent. About 11,500 years ago, at the beginning of the Holocene, there is general climate warming, and wildfires became even more frequent, especially as us humans began making an impact on our environment. Early humans, and even much later humans living today, clear the land via burning for easier hunting at first and then for agricultural purposes. Prior to us, say prior to about 1.3 to 1.8 million years ago, fire was primarily started by lightning, as pictured on the left, and volcanic eruptions, as pictured on the right, with a lava flow setting vegetation on fire. 13.2 Wildfire as a process. Fires are a self-sustaining, rapid, high-temperature biochemical oxidation reaction which requires fuel, oxygen, and heat. Another way to think of fire is that wildfires are another way to remove vegetation, and that fires are the reverse process of photosynthesis. The image to the right shows the trinity required to sustain fire. Each side of the triangle is labeled as either fuel, oxygen, or heat. Wildfire smoke may be the most widespread, annoying part of the wildfire hazard. The smoke is composed of gases, ash, and soot. The major gases released are water vapor and carbon dioxide. And the minor gases released are nitrogen oxides, carbonyl sulfide, carbon monoxide, methyl chloride, and hydrocarbons, including methane. Really nothing there that I want to breathe in except maybe some water vapor. Besides the gases, there are also ash, which are mineral compounds that may contain calcium and or iron, and soot, which is the unburned carbon. Still don't want to breathe in this stuff. The image to the right shows that some black wildfire smoke looming over a very beautiful home. Wonder how long that home will last. There are 3 phases to a wildfire. Pre-ignition, where fuels are prepared for the next phase. Combustion, and the last phase is extinction. The images are representations of the 3 phases, with the top image showing the edge of a fire where the next fuel to be burned is being heated and scorched. The pre-ignition phase. The middle image is a full-fledged, very big and dangerous wildfire with a definite combustion stage. And the bottom image is of where a fire was burning, but is not any longer. The extinction phase. So going through each phase in a little more detail. First, the pre-ignition phase. In this phase, heat radiating from flames causes both preheating and pyrolysis in advance of the fire. In preheating, fuel loses water and other volatile compounds, which are compounds that are easily vaporized. In the image below, you can see some of these volatile compounds leaving the twig nest that is about to combust. The other part of the pre-ignition phase is pyrolysis, meaning heat divided, which is the same as scorching, but pyrolysis just sounds so much cooler. Pyrolysis is a process that chemically degrades fuel to make it easier for burning. The heat divides or splits large fuel molecules and produces volatile gases, mineral ash, tars, which is composed of phenols, polyaromatic hydrocarbons, and heterocyclic compounds. Char is what remains. By the end of the pre-ignition phase, the fuel achieves temperature and water content favorable to ignition. The image on the right shows char on toast. Next time you see burnt toast, you can say, "That's some nice pre-ignition." Or, "Look at that pyrolysis." And I'm sure that will impress all your family, friends, and associates. So pre-ignition prepares the fuel for the next phase, combustion. This phase begins with ignition. In contrast to pre-ignition, which absorbs energy, combustion releases energy. The external reactions liberate heat and light. The image to the right shows some bright combustion behind some trees that are undergoing preheating and pyrolysis. Ignition doesn't always lead to wildfires. Why? Take a moment to form an answer in your mind. If you want a hint, look back at the fire triangle of fuel, heat, and oxygen. Usually, a wildfire has enough oxygen because, air. Also, once ignition is achieved, heat usually isn't a problem either. But, is there enough fuel? Why might there not be enough fuel? So, repeated ignition events lead to sustained combustion. There are a couple different types of combustion. 1, flaming combustion, and 2, glowering or smoldering combustion. Flaming combustion dominates early in the fire and is a rapid high-temperature conversion of fuel to heat. It is characterized by flames and a large amount of unburned material, as it is hindered by a blanket of non-combustible material that forms as volatile gases are removed from the fuel. Glowering or smoldering combustion takes place at lower temperatures and does not require pyrolysis for growth. but it does require preheating. The ultimate product of smoldering combustion is charcoal. The top image is a picture of what type of combustion? Flaming or smoldering? Right, flaming. Look out, dear. The bottom image is a picture of what type of combustion? I bet you said smoldering. Did you? Heat transfer in wildfires. As mentioned previously, ignition is not a single process, but occurs repeatedly as wildfire moves. Heat transfer occurs as conduction, convection, and radiation, with convection being the most important, radiation being the second most important, and conduction not mattering much at all. The images are here to help remind you that what conduction, convection, and radiation are. Conduction is energy transferred by direct contact, as in the metal handle of a pot gets hot when the pot is heated. That's why my pot handles are insulated. Convection is energy transferred by the mass motion of molecules, like water boiling, or moving in the pot from the hot source at the bottom to the cool surface and back down. This occurs with other fluids. Remember convection cells in the metal? Also remember air rising and falling in the Hadley circulation cells? Also happens more locally with storms, and happens with smoky air too. Convection cells are established in wildfires as heat increases surface temperature of the fuel. Gases become less dense and rise. Rising gases remove heat and combustion products from the zone of flaming, which pulls in fresh air to sustain combustion. The last heat one is radiation, which is energy that is transferred by electromagnetic radiation, which you hopefully remember includes light waves, as well as waves beyond our visual spectrum. The next several images we will look at heat transfer in different wildfire scenarios. The first scenario is just a wildfire on a flat surface with little to no wind. Cool air, oxygenated air, is being sucked in at the bottom in indrafts as the hot air and smoke rise. Radiant heat is radiating out from the flames in all directions, heating all surroundings, but critically, it is heating the next batch of fuel. The preheating and pyrolysis of the next batch of fuel prepares the path for the wildfire to advance. It is not moving very quickly as the convection heat transfer is moving most of the heat up and away, and the radiation heat transfer is fairly far from the trees that look like they are the next in line for ignition and combustion. In this next scenario, the land is still flat, but a hefty wind is pushing the flames toward more fuel. Radiant heat is closer to the trees. Convection is also heating the trees. The wind may even carry sparks ahead of the main fire front and start spot fires. This fire is moving much faster than the previous scenario. Wind helps convection and radiation transfer heat for preheating and pyrolysis to the next trees to ignite and combust. This last scenario is a wildfire on a hill. This fire is also moving fast, as convection and radiation transfer heat to the next trees to ignite and combust, and often there is wind associated with a hill slope, which helps the heat transfer via convection and radiation, causing the fuel ahead to undergo preheating and pyrolysis even faster, and so the wildfire moves even faster. Here are all three scenarios just to compare. See how wind and slopes help with the heat transfer to the next fuel? See why they move faster? Don't memorize. Understand the process.